All right, let's go ahead and go backwards. So we're going to express the sum using summation notation. So that means you're going to have this capital sigma. So from n equals somewhere and some sort of a stopping number. So this one's, it's kind of simple. It's just 1, 2, 3, 4, 5, 6, all the way up to 20. So let's go from 1 to 20 of just n. And you can always test it to see if you get the same sum back, and for this one we do. So on B, it's going from 1 all the way up to 8. So from 1 to 8. And then what are we doing to each of those numbers? Well, we're raising them to the third power. It's n to the third. You don't have to use n if you don't want to. You can use k or whatever letter. Just probably not e or x. Okay, now this one, it's a little bit different. And so the key for this is to kind of look at that, that term there. So we're going to start with n equals 1, and since it's 2 times 12, we're going to have it go all the way up to 12. And then this right here is kind of telling us how they got each of these numbers. It's just 2n minus 1. Okay, and then this last one, we're going to start with n equals 1. And we have 1, 2, 3, 4, 5, 6, 7 terms. So we're going to stop at n equals 7. So if you look at it, it's alternating in sign again. And the first number is positive, so that makes it the -1 to the n minus 1. And it's getting multiplied by a 1 over 3. But I want my first number to be a 1, so that also has to be n minus 1. Okay, so that's how you can kind of go backwards. So now we're going to play around with the sums themselves and see what you can do, especially when the sums are large. So sums have their own properties. So with this, so like number 1, if you've got some sort of a constant in there, you can just pull the constant out to the front and then do the sum on its own. If you have more than one term in there inside the sum, you can break it apart and do the sum of each term. And that's both of those are especially useful. The summation formulas, this is what you would use if your sums are rather large. So like if you're going from 1 to 100 or 1 to 50, that would be quite the tedious task to have to write out each term and then add them all together. So instead we can use these. So if you're just summing up a constant, it's like c plus c plus c, or 3 plus 3 plus 3. It's just whatever that constant is times the stopping number. So c times n. If it's just a k, your formula is n times n plus 1 over 2. If it's k squared, n times n plus 1 times 2n plus 1 over 6. And then if you're summing up k to the third, that is n squared times n plus 1 squared over 6. Oops, sorry, not over 6, over 4. Okay, so let's try those out. So for here, it's just a 5, that's the constant, so we're following formula number 1. So 5 times 40 gives us 200. That's a lot faster than doing 5 plus 5 plus 5 plus 5 40 times. All right, part B, we're going to use a property on this. We're going to start with that first one. We can split it up because we don't have a formula for quantities. we have it for individual terms, but not something with a minus or plus in between them. Oh, and I think somebody's at our front door because my dog's going crazy. Oh well. So just split it up. And then we can use that first property over here. I've got a number being multiplied in, so I can pull it out. And then I can use the summation formulas for each of these. So the 3 just stays as a 3. And the summation formula for k is n times n plus 1 over 2. So I'm going to take the 20 and plug that in for n. So 20 times 21 all over 2. And then minus, now the 7 is just like example A, it's just your constant. So minus 7 times 20. So if you start to work it out, we have 630 minus 140, which gives us a total of 490. Okay. For the k squared, I'm just going to follow the formula for k squared. So the 14 is your n. So 14 times 15 times 29 all over 6. So if you start to play with this, you can take a 2 out of the 14 and the 6, and then you can take a 3 from the 3 and the 15. So 7 times 5 times 29, or 35 times 29, which is 1,015. Okay, part D, this one's a little different because if you notice, the starting number is not a 1. In order to use these formulas, you have to start at 1, and this one doesn't. It starts at 3. So we need to be a little bit creative in how we get its total. So since I know the formula for 1 to 30, I'm going to start there. Because I can figure out what this is just by using that formula right there. But we're not going to do that just yet. I'm going to play around with this because I want this to come out of here. So I need to plug in k equals 1. And then I'm going to plug in k equals 2. And now I would have to plug in k equals 3, and then 4, 5, 6, 7, 8, 9, 10, 11, all the way up to 30. Well, that's what this sum represents. So I have left to plug in from 3 to 30 for k. So the right side is just 3. I don't know what this sum is, so I'm going to leave it alone. But over here on the left side, I can now use that formula we talked about earlier. So my n is 30. So if I reduce this side down, that's 465 equals 3 plus the sum k equals 3 to 30. So now I just do the algebra. I just solve for this thing. So just minus the 3. So the sum from k to 30 of k is equal to 462. All right, so that's going to do it for 12.1 with these sequences and these sums. So in the next video, we'll be talking about section 12.2 and working more with just different types of sequences and sums.